workshop. Sorry about that. So today I will report that's old talk, semi-implicit method for the fifth field equations. So this is a joint work with Professor Li Dong in Hong Kong, USD. Li Dong originally from UBC, and he moved to Hong Kong, UST like 2 years ago. And Professor Tao Tang, and Tao Tang, he moved from Hong Kong Baptist University to the Shenzhen, like also 2 years ago. So, this is the outline of the talk. So I will introduce energy stable schemes for the fifth field equations. So one of that's stabilized semi-implicit schemes. And this talk is very technical, so we give the proof. So if you feel that's very boring, then you can work on your own job. So, and then we introduce the high order time-stepping method. So this is an equation we want to consider. So that's a Cantor equations, and that's a very famous equation for the gradient flow problems, and also works for the multi-phase flows. Many professors here work on the multi-phase flow problems. So that's a fourth order equation, fourth order parabolic equation with a nonlinear term. So this FU, we use a very simple Helmholtz energy. It's capital FU. That's a double potential used quite often in practice. And then this small FU in the equation is the capital FU takes the first order derivative with respect to U. So we get a third order polynomial. So this is an energy functional we want to consider. The Cantor equation could be regarded as H-1 flow of this energy functional. So this is called the Helmholtz free energy, and that's a surface contribution. So with different select of the Helmholtz free energy, you have different models in material sense and for the multi-phase flows. So now we only consider this very simple double potential. And this equation, Cantor equation, certifies this total mass conservation. And in particular, if we have this mean zero as with initial data with this mean zero property, then the solution also have this mean zero property. So in this work, we only consider the initial data with mean zero. Then we can define this fractional Laplacian when this S is negative. So we need to use this assumption, the initial data with mean zero, because we want to define the free side as a zero mode. This Cantor equation certifies this energy identity. So if you don't want to have this gradient inverse operator, so then it's better to have this formula. So this formula tells us, so this energy is non-increasing in time. Right? This energy identity gives us this energy non-increasing property of these Cantor equations. So when we design the numerical schemes, we should consider this property. And also this energy identity gives us a prior control of the H1 norm of the solution. So in the proof of the theorem, we need to use this H1 norm control, this result from this energy identity. Okay, now let's consider the numerical discretization of this Cantor equation. So we will have high order time-stepping method. Now we consider the first order method first. So a very straightforward treatment is to use a backward Euler discretization. For the high order derivative, we use implicit treatment. And for the nonlinear term, we use linearization. then for this backward Euler with linearization for the nonlinear term, this numerical scheme, we give a large truncation error, and we could not guarantee the NG stability. So we need to use a very small time step to guarantee the NG stability. What is NG stability? That is, the NG non-increasing in discrete time. We call that NG stable numerical schemes. So then a very simple remedy is to add a stabilization term to this backward Euler treatment. So the numerical scheme becomes to the equation 9. So we add this first order stabilization term. So you could say this term is order tau, right? So that's first order stabilization. So A is the stabilization constant. So that's a positive constant. So of course we have other works. So by Bertuzzi, she will give a SM 45 minutes talk in this SM this year. And also, so this work we will cite later. We also use their result. And also Shen Jie and Yang Xiaofeng's work in 2010. So they have they also worked on different stabilization schemes. And also for this, I want to see more words on the NG stable numerical schemes for these Cahillary equations or other phase field equations. So there are many other methods. NG stable method. So, for example, the very efficient convex splitting schemes, okay, and also use discrete gradient flow schemes. So stabilization method is one of that. So that's the first order, and later we consider the second order stabilization. Okay. So then, in this Professor He Yinyan and Liu Yunxian and Tao Tang's work in 2007, so they proved when A satisfies this condition, so A is greater than this formula, so they can prove the NG stability in discrete time. So, but look carefully on this formula 10, this inequality 10. So when we compute the UN plus 1, that's current numerical solution, so we need a stabilization term. But for the inequality 10, so A is dependent on current numerical solution, right? So that's a drawback for this analysis.
This scheme,
yes.
can we prove that Boltzmann is bounded?
Yes, that's a good question. So then this inequality implicitly requires, so the numerical solution has some arithmetic bound, right? So that's a difficulty. So they could not prove that, in fact. So, and also that's a drawback for their analysis. So then I work on this problem since 2009, and we try to improve this inequality and try to prove the arithmetic bound since 2009. And we, of course, at the very beginning, we work on another equation, not Cahillary equation. But finally, so we work on because this Cahillary equation is so popular. So then we move to the Cahillary equation after several works. So we use other NG stable method to solve these problems because we could not solve this. We cannot prove this numerical solution is arithmetic bounded. So just now, as Professor Bao asked, so that's implicit. Ask this arithmetic bound assumption on the numerical solution. So in fact, for the in practice, we could assume some boundness of the PD solution, but we could not assume the boundness on the numerical solution, right? So and another treatment is by Shen Jie and Yang Xiaofeng. They assume this ellipse, they give this ellipse assumption. You know, this f prime u, fu is a cubic polynomial. So the first order derivative of this cubic polynomial is a quadratic polynomial. And so when u is, in the whole real number site, so you could not prove the boundings of this nonlinear functional, the derivative of the nonlinear function. So, and in their work, they have assumed this condition. So they just give a modification on the nonlinear term, right? So they truncate this nonlinear function. So that's implicitly requires a arithmetic bound of the numerical solution. For example, if u is bounded from -1 to 1, so then on the closed side of the domain, so they could have the boundaries of the nonlinear function. So, and roughly speaking, so all pure analysis requires arithmetic boundaries on the numerical solution. So that could not be avoided, and that's our target to remove. Our target is to remove this technical restriction and establish a more reasonable stability theory. So after several years work on these problems, so in 2016, so we gave a first result. So in this SAM numerical analysis paper. So that's the main theorem of this work. So we call that unconditional energy stability for the Cahillier equations. So then consider the stabilization numerical scheme, none, with this diffusion parameter. The small diffusion parameter is greater than 0 and less than 1. So and then we have some assumption on the initial data. So with some regularity requirement. So U0 is in A2 with mean 0. And then we have this initial energy. So that's a main result. So there is a constant, only depend on the initial energy. And A is greater than, essentially A is greater than this term. So nu inverse log nu square. So we can have this discrete energy stability. But because this is the first, attempt to this problem, so you can see the essential term, nu inverse, is quite large because nu is very small, right? For the small diffusion parameter, nu is very small positive constant. So then nu inverse and log nu square is quite large. So, and in practice, we do not need to have such large constant as a stabilization constant. So in practice, A is when A is greater than 2, greater than or equal to 2, that's enough. You can have a very good result. So why? Because the Cahillier equations. So U is almost everywhere. U is almost all the time U is between -1 to 1, and in fact, in our another job with Li Dong in GDE, we can construct a counterexample such that the initial data is between -1 to 1, and immediately it can larger than 1. The norm can be larger than 1. But for a long-time simulation, the numerical solution is bounded by the norm of the numerical solution is bounded by 1. So anyway, so that's why A is from the previous non-inequality. When A is greater than 2, that's enough. But we could not assume that. So we have counterexample, right? So then mathematically, we should follow this inequality. That's the first attempt, and we have further work. So we try to prove A is dependent on only order 1 constant. Now it's still ongoing. Okay, so this talk we will mainly prove this theorem. Okay, give the proof of this theorem. So this result could be also extended to the MB equations. So with loop selection. And for MB model without loop selection, we do not need to have this inequality. So we have the joint work with Li Ju and Hui Zhang and also Li Xiao. So A is only greater than 1/8, that's enough. So because for the MB model without loop selection, the nonlinear function have some good properties. Okay, so that's MB equation with loop selection. So we still is this stabilization term. So you can see that's a stabilization term. And in Tao Tang's paper in 2006 with Professor Xu Chuanju in Xiamen University, so they can prove when A is greater than this inequality, so they have this energy stability in discrete time. So here you can see the implicitly they require the gradient U has a bound numerically. So our result is here. So A is also essentially greater than this term. So we have this energy stability in discrete time. But U0 should be in H3 with mean 0 because the gradient U in the nonlinear functional. Okay, now let's look at the proof of this theorem for the Cahillary equations. So the proof mainly use this inequality. So we have the H1 period boundness of the solution. Right? The numerical solution, we could have the H1 boundness. But we don't have this R infinity boundness. So, but we can have a log correction from this inequality. We could have this log correction, and then this R infinity boundness will depend on the the small diffusion parameter nu. That's order 1 over nu, and 1 plus this order 1 over nu stuff. With this log correction, so we can have the R infinity boundness. So in fact, our proof based on lemma, the lemma requires this UN plus 1 HS norm boundness. So S is greater than 1. So later we prove H3 over 2 norm has a boundness. And then with H1 norm boundness from the energy stability, so with this log correction, we have this R infinity boundness of the numerical solution. So then we match the coefficient, and then we can have the boundness for the stabilization constant A. For any S bigger than 1. Yeah, but we can prove the H3 over 2 norm of that, right? So we use S is 3 over 2. So then this H1, we have the H1 boundness. So with this log correction, we can have the R infinity boundness. That's our idea of the proof. Okay, now first we prove this boundness of H3 over 2 of the numerical solution. So we have this lemma. So and also H1 norm, that's from the energy. So we use a spectral galectin in space. So then the numerical scheme none could be written in this form. We can write in this. That's operators. Okay, we can write equation none in this form. So then let's prove the lemma 1. So in the free side, so we have in the free side for this equation 18. So we can have we want to take the norm of the 3 over 2 norm, right? So then we in the free side, the operators takes as a free side. We have this inequalities. Now how to get this inequality? So it take the different denominator of this fraction. So they have this encoding. And also like this one. For example, you drop this term, then you have this encoding. Okay, so then for both sides, we take the H3/2 norm. So then you have this encoding by using this. You put this term here, and you put this term here. So you have this encoding. And from this, F is U cubic subtract U. Okay, this U cubic subtract U. And then from this, that's L2 norm to this 4/3 norm. So we use substitutive embedding from this substitutive embedding formula. So you can have from this step to this step. And then that's a part of the, the ng functional. If you take the derivative, if you take the integration of that, that's part of the ng functional. You can enlarge that, then you have this encoding. So that's the first part of the lemma. Basically, we need to use this substitutive embedding. Then you can have this lemma. Our second part is from the the ng. Is from the ng encoding. So and also we assume as a un we have the infinite boundness. Also in the later proof, so we can assume we use a mathematical induction. We can assume the previous step we have the infinite boundness, right? As U0 we had boundness, then we prove U1 we had boundness, then we prove the later case, right? So with the UN boundness, so we can prove the UN plus 1 H minus 1 boundness with the ng stability. That's the second part of the lemma. And also we need the lemma 2. Lemma 2 tells, so you can see the lemma 2. Lemma 2 is very easy to prove. That's a basic calculus proof. So lemma 2, you can look at the form inequality of this lemma 2. So here, if you move this term to the right-hand side, okay, so and take this common term, so then if this, that's a and nu, that's constant A, and nu, that's diffusion parameter, and tau, that's time step. Okay, if this term greater than this term, so then of course, so the En plus 1 is less than En, okay? So we want to prove, basically in the theorem, we want to prove this term is, we select some A such that this term is greater than this term. And A is independent on the time step. That's our requirement. This proof is very straightforward. You just use usual L2 inner product with this term, minus inverse, Laplace inverse of UN plus 1 sub to UN, and multiply on both sides, and takes we use a periodic boundary condition. So then with this green formula, you can have the following equality. And then further collect that. So and use fundamental theorem calculus, and you can get original ng functional, right? Takes the integration. That's a part of a harmless free energy, the part of the ng functional. So anyway, so finally you get the lemma. So that's not very difficult proof. Now let's try to prove the theorem 1. As I mentioned, so the proof is to prove this term is larger than this term. For UN infinity, so we use a mathematical induction, right? We can assume this is bounded. And of course, we need to prove the base case, U0 is bounded. And then for UN plus 1, we use a previous inequality. Right? We use this H1 bound, and then use a log correction. So then we have the infinity bound. So this is bounded and with some inequality, and this is bounded with some inequality. And we select A such that this is larger than this term. And how to choose A smartly, and such that A is independent of this tau. That's our proof. Okay, that's proof of our theorem. So as I mentioned, we prove that use mathematical induction. So for the mathematical induction, we should prove the base case first, and then we prove, well, n equal to k. We assume n equal to k, that's satisfied, and then we prove n equal to k plus 1. So the inequality is satisfied. But now, in our proof, we prove we assume the statement is true for n is greater than or equal to 1, and then we prove that's for n plus 1 first. And for the base case check, so because let's use the same procedure, so then we prove that at the back. Okay, we prove the base case. We check the base case after we prove this when n equal to k plus, from n equal to k to n equal to k plus 1. That's our strategy. Okay, step 1. So that's induction step. When n goes to n plus 1, right? N equal to k, that's 2, and n equal to k plus 1. We want to prove that. So as mentioned, we assume the induction is hold for n greater than or equal to 1. So now we verify statement for n plus 1. So from the lemma 1, so un plus 1 has a boundness with h3/2 norm. Right? That's lemma 1. That's from the lemma 1. And then from this, if we can prove this En is less than or equal to E0, initial energy, so then we can prove that, right? We can prove this Un plus 1 is bounded by this. In fact, we shall prove not only En plus 1 is less than or equal to U0. In fact, En plus 1 is always decreasing, so not increasing. So bounded by En. That's our proof. So then from lemma 2, as I mentioned, so we need to prove this constant, this formula with this constant A is greater than the boundness of the Un and the Un plus 1. So we need to prove that. After we prove that, so we can prove this En plus 1 less than En. Right? So now let's prove that. We need to select A smartly. So we shall use the log interpolation inequality, as I mentioned. So we have H1 boundness with a log correction for H3/2. So we have the infinity. So now we change this F to be Un. So you have this inequality. Right? Un is bounded by this 3/2. And Un is, we have this H1 non-boundness. So then you can have this Un infinity boundness. So then H1 norm, so that's bounded by this term because we have the, we have proofs as a t equal to n, at Tn step. So we have the Ng stability, right? We assume that. So then you have this boundness by the initial energy. So that's an assumption on Un. Un's H1 norm is bounded by the initial energy. And then Un H3/2, that's boundless. That's from the mathematical induction assumption. Right? We assume Un is bounded by this. And we want to prove Un plus 1 is also bounded by this. Right? Okay, so then we get all the terms. This term bounded here, and this term is bounded here by the mathematical induction. So mathematical induction assumption. Okay, then we further collect that, and then we have this term. We define this term is dependent on only nu and A. Okay, we define that by M0, and this term will have the tau term. That's a time step term. So. And for Un plus, okay, so we further write that to this term. So M0 squared, and then this term we have nu inverse and log tau. Okay, so now we drop this 1 over a. So because we assume a is greater than 1 first, okay? A is greater than or equal to 1 first. And for un plus 1, this L infinity bound, we use the H1 norm that's boundness from the lemma 1, the second part of lemma 1. And then this H3 over 2, that's that's the first part of lemma 1. The first part of lemma 1 is bounded by this un infinity, so we can change to this term we put here, and then this H3 over 2, so we put here. Let me see. This should be un. This should be un, I think. Okay. Anyway, so finally we will further collect that un plus 1 is bounded by this term with m0. M0 has only related to a and nu. And okay, these terms only related to a and nu, and also this term only related to a and nu. So we only have one term. Also, we have one term related to time step tau. So we need to drop this term, in fact. Okay, then the un and un plus 1 infinite boundings. We have this. We collect we add them together. So we have this formula. So we need to show. So we want to show this, right? If we could show, we drop this 1/2. A plus this term is greater than that. So then this equality holds, right? The first step, we prove a plus this term. We do not need to this constant 1/2. So a plus this term is greater than this infinity boundings of un and un plus 1. So then how to prove that? So we have, we prove this inequality. So we separate that to two cases. When this term, the first term is greater than this term, so then we choose A with this formula. We choose A is larger than this nu inverse, and A, we have this A and nu. We don't have tau here. Then clearly, of course, that's for nu is greater than 0, less than 1. For nu is greater than 1, so sufficient to choose A is order 1 constant. That's enough. So anyway, essentially, A is greater than this nu inverse log nu square. That's enough to have this inequality. So that's case 1. And case 2, so when this is less than that, so we can also select. We select A, certify this inequality. Don't forget, so this M0 only related to A and nu. So we don't have any relation with tau. So you further select that, and you collect that, and you solve A, and essentially A is also greater than this nu inverse and the log nu square. So that's the main part of the theorem. So then we have finished the proof for the induction step. So we check the base step. We verify for the base step n equal to 1. That's from U0 to U1, right? So then for U1, so we have this, by lemma 1, we have this inequality, right? So then that's true. So now we only need to check the energy as the first step is less than the initial step. So then we need only check this inequality holds. And we follow the previous steps as an induction step, so you can get the result. That's quite same. You just change un plus 1 to u1 and un to u0. That's enough. And why we need u0 is bounded A2 is in A2. So that's from this inequality requirement. So we need u0 is in H2, the regulatory requirement. Okay, so then this completes the proof, the base step, and then the induction step. So essentially, as I mentioned, when A is sufficiently large, so essentially that's the essential term. By adding this stabilization term, so we can have unconditionally energy stability. Here, A does not depend on the numerical solution boundness. Right? A is only dependent on the diffusion parameter nu, but strongly depend on that. Further remarks for similar result for MBE. So we do the same analysis, and also we can extend that to 3D catheter, but that's a little bit difficult because in 3D, so that's H1 supercritical. So and we have the result in Professor Jin's journal, CMS. And for that's the result for 3D catheter. So A depends on nu minus 3, power minus 3. So then have this energy stability. And for high order scheme, so we should at least get the second order scheme for the numerical computation. So we do have the second order scheme. So that's a second order stabilization formula for the paper in Xu Chuanjie and Cao Chang's paper for MBE. Okay, that also works for the cantilever. So then they use this numerical scheme. So with this second order stabilization, so they can prove so the modified energy. So the modified energy is like En tilde, n plus 1 tilde is less than En tilde by adding the second order truncation errors. So that's their result. Our result, in fact, we can prove for if A is greater than this nu, some formula on nu inverse, so we have this energy inequality. So this energy is not modified, right? You can have some, symmetric properties. So that's U n plus 1 subtrate U n, that's U n subtrate U n minus 1. For in Cao Chang's paper, they could not have this inequality. So, and roughly speaking, when the time step, they have some constriction on the time step. When time step tau is less than 8 times nu, so they have this stability. Okay, so now if we don't add the stabilization, so if we A equal to 0, we don't have the stabilization. So that's a BDF scheme, right? So then we also have a result when this time step is quite small. So nu like this, that's a regime we want to consider for the field equations. Nu is less than 1. It's quite a small constant. So when tau is dependent on nu with power 9, that's quite small constant. So we have this energy stability, right? That's why we need the stabilization term for when we design the energy stable schemes. We can use a larger, we could use a larger time step to do the simulation. Okay, so this result has recently been extended to the, we use the spectral Galeckin in space. Then this result has been further extended to the local DG method by Professor Qiwang Shu and his visitor Songhua Lin in a paper in GSA this year. So that's the result. A is highly dependent on the epsilon here should be nu. Okay, the small diffusion parameter. Okay. So that's from the encoding. So that's difficult to. Also, Qiwang said. So do you have a further result? So their reviewers also always ask them the question whether you have this very large constant, right? So I think I stop here. Thank you.
Thank you. So if you add specialization,
yeah.
will your A depend on mesh size or does it depend on mesh size?
No. So for our result, so A is only depend on the diffusion parameter. And in fact, in the practice, A is a constant, that's enough. 2, that's enough. Do the real practice computation. Yeah. So why we have this start very technical analysis? Because we don't want to ask A is depend on the time step, right? That's why we have this very subtle analysis. Yes. Okay.
Here you consider the coordinate equation with constant mobility.
Yes.
In some cases, people also are interested with the coordinate equation with degenerate mobility.
Yeah.
Do you have the similar results?
No, we only have one result here. So now our ongoing work is try to get a better constraint on A. So remove this that's a new inverse stuff that's quite large. So we want to get order 1 constant. So our result, we want to have a result. A is depend on nu over tau stuff. 1 plus square root of some constant plus nu over tau stuff. Right? When we have large time step and a small diffusion parameter, so that's order 1 constant. That's our, we want to have this kind of result. That's still ongoing. And for other difficult problems like degenerate mobility stuffs, we don't consider that at this moment. That's even more difficult, I think. Yeah.
For one specific numerical example, can you find the sharp bounded A using numerical method?
So as I mentioned, so their result, the Tautong's result. So here, so if U has a boundness by 1, okay, so then you can have A is greater than 3/2. That's enough. So in fact, in the real practice, when A is larger than 3/2, that's enough. We can have very good numerical results. Okay. In practice, in mathematical analysis, that's one story. In the real practice, that's another story. Right?